Hi, my name is Jeff Clarke, and I'm with CD Aviation Services. I'm the APU Technical Support Manager, and today we're going to be discussing the 36 series APU made by Honeywell. We're going to try to get familiarized with it and things to look for and troubleshooting, things of that nature. So what we're going to be talking about primarily is, again, the GTCP36-100 series, which is like what you see here on the left, as well as a GTCP36-150. And you'll find throughout this presentation that these two APUs are pretty much very common. There are some differences, of course, with the hot section on the 150 as opposed to the 100 with the single combustor. However, the primary APU pretty much functions the same, with some additional modifications that Honeywell made to the compressor on the 150, which I'll be discussing. So there's an application chart as opposed to what APUs and airframe designations are. So if you see your aircraft up here on the left-hand side of the column, you'll see the APU model that corresponds with that APU. Now you'll see the one for the Hawker 800, 900, highlighted in red is the 150W. Now, the W is one of the first APUs, or first 150 series APUs that Honeywell manufactured, and was pretty much initiated as a generic APU. For example, if you have an aircraft that maybe you want an APU added to it under an STC, Honeywell provides the 150W for that sort of thing. It's a very stripped down basic model 150. Yes, it's primarily in the Hawker 800, 900s. However, you may see that in the Falcon 20 installation. There are some Citation installations. That's the one APU, the 150W is the one APU you may find in several, three or four or five even different airframes, pretty much installed under STCs. But other than that, these other APU models are pretty synonymous with that airframe that's listed. So if you see your airplane up here on this list, and you see your APU in the column next to it, when I get to those, you can kind of get an idea of what we're talking about. When I mention 150F, that would be a Falcon 900. Okay, so these APUs is pretty much, they're controlled by an electronic control unit, both APUs, 36-100s and 150s. So pretty much in the cockpit, pilot lights off the APU. He primarily has two indications, RPM, EGT. He may have some low oil pressure light indications, things of that nature, because the ECU pretty much does everything. It controls it, makes sure it's operating in a safe range of temperature and speed, and it has protective features of overspeed protection, over temp protection, low oil pressure protection, high oil temp, and there's an overcurrent protection in the event the ECU itself starts to get a little iffy on whether it can perform the function it needs to do. It may have an overcurrent shutdown. So if any of these protective shutdowns here on the left occur, we would have to interrogate the ECU or in some fashion, or all a little different, on what we got to find to determine why it shut down. All right, because this ECU, yes, it's made to primarily operate the APU on its own, but its main function is to protect the APU at all costs. And you'll see there's all their variations of the ECUs. For example, it's what you see in 100EG is just a basic box with two Cannon plugs. You have a fault panel that can help you out with the troubleshooting. The 150W, for example, again, it's another box, and these are typically not mounted to the APU. They're mounted up in the airframe, remotely located. And if this APU trips or shuts down, there's three little dot lights down here at the bottom of the ECU that flip over, and you can kind of use whatever code it's showing you to determine to help you troubleshoot the APU. Some APUs, like the CX, F2M, and RJ, have a rack mount ECU. It has a digital control in the front. Very nice ECU to interrogate. And some of your ported shroud, these newer APU models have a rack mount ECU, and you have to do a laptop download to determine what's going on. So the main two things I mentioned that this ECU needs to see is temperature and speed. And that's with any kind of a jet engine, basically. We're always concerned about overspeed and overtemping jet engines, and that's no different for the APU. So we want to talk a little bit about how this APU is controlled to keep it within a proper speed and proper temperature. All right, so and we're going to be using a 36-100 series as our example. So there's our cutaway of that, and I'll get more into that. But here's the control systems. And again, your cockpit doesn't have much in it. This would be kind of what you would indicate in the cockpit. The electronic control unit, so all the functions between the cockpit and the APU have to go through the ECU, in and out of the ECU. All right, so fuel control unit is mounted to the front of the gearbox, as you see here, and it's electronically controlled by the ECU. There's a cannon plug on the front of it. The load control valve, which is what opens and closes the air, bleed air off of the APU to supply the airframe needs. That's mounted to the plenum, so that's getting bleed air off the plenum. And again, that's electronically controlled by the ECU, just like the FCU is. All right. The two things that provide the indication. So we have a monopole, a speed pickup on the gearbox. This is considered the gearbox. It's a very crude drawing, but it gets the point across. This is our gearbox with the speed getting indications off the main gear in the gearbox. This represents the compressor wheel, which is this piece here. This is the turbine wheel, as you can see, is directly coupled to the compressor. Here's your turbine wheel. So the turbine wheel has the shaft on it, the compressor slips over the shaft, and it's directly splined. So whatever speed the rotating group goes, it goes together, same speed. And back here in the tailpipe is our thermocouple, again, going to the ECU. So the thermocouple temp is going to ECU, speed is going to the ECU. The ECU takes that information and makes fuel and bleed air adjustments to keep the temperature good and keep temperature good and keep the speed good. Okay, so let's say this APU is running, low control valve is closed, power does not need bleed air, and it's just running at 100% speed, which is what this ECU needs to maintain. This ECU's always got to keep this APU running at 100% RPM. All right, and of course keep it within a safe temperature. So we're just running, no load on this APU. The generator is offline. Let's say the APU is just running. And everything's fine. ECU sensing a nice, good temperature. Well, now we add generator load, which is on a big generator mount pad here on the front of the gearbox. Right, there's a big generator that typically mounts on these gearboxes or these APUs. When you turn electrical load on, that puts a mechanical load on this rotating group, or just a load of it producing electricity slows the rotating group down a little bit. So the RPM is sensed here. The ECU says, well, it's dropped a little bit below 100%, so I need to get the speed up. So it does that by adding fuel to the fuel control unit. It tells the fuel control unit to add fuel to the combustor, right? And now our temperature does rise a little bit because of that added fuel, but because the thermocouple is sensing that it's still within a good, safe operating range, there's nothing that needs to be done. Everything's just fine. It's just temperature increased slightly. And we have a mechanical load, which slowed the RPM down. So the ECU told the fuel controller to open up, add fuel. Well, now the pilot's running, and now he says, well, I need some air. I need to do a main engine start, for example. So he's going to open up this low control valve with a bleed air switch in the cockpit. The ECU is going to open up the low control valve. All right. And now the APU is going to do a main engine start. So all that air is rushing off this APU. And that's a large valve. It's like 2.5-inch throat diameter. So we're dumping a lot of air that we typically use to run the APU. We're using a lot of air to support the airframe need. So when you pull that air off of that APU, the RPM of this rotating group really wants to fall. It drops quite a bit. Well, immediately the monopole senses a speed droop. ECU then says, I need to add more fuel. It adds fuel to the fuel control unit, tells the fuel control unit to add fuel, adds flame to the fire to get that speed up to 100%. Now as that speed's in getting up and added fuel's coming in, our temperature, our EGT is climbing really high. So here comes the protection. So now the thermocouple is telling the ECU we're approaching like 665 degrees Celsius, which is a pretty common number for these ECUs to actuate the valve. Thermocouple is reading a high EGT. Well, the ECU needs to cool that down. It's not going to take fuel away to lower the RPM or lower the temperature because it needs to maintain 100% speed. So the fuel is going to keep coming. So the only way you can keep the temperature down is for the ECU to meter the low control valve close a little bit, like don't open so much. So it'll start to shut the valve until the temperature becomes within a safe range. And that's what happens. So if the air is still needed, the ECU is going to try to give all the air it can to the airframe need. However, its ultimate job is to protect the APU from overspeed and overtemp. So it'll close this low control valve off to keep this temperature cool, and it can rob you of all your air if your hot section is not as strong or if the APU is not as proficient as it once was. Okay, so what happens is your your turbine section gets distress, hot gas distress, right? Your turbine nozzle gets hot gas distress. It's not as efficient as it used to be. So a lot of times this temperature will climb quicker than it was when it was first had a hot section. And therefore it wants to shut this valve sooner rather than later and robs your airframe of your air. So the phone call that I get from pilots isn't so much that my APU is running hot, because it's always trying to maintain a good temperature, and that's what you'll see in the cockpit. It's just that I just don't have the air supply that I used to have. My main engine starts are long and hot, and my air conditioning in the cockpit isn't so good. So those kind of the calls that I get. So we would, perform some operational checks and see where we're at with this APU. So that's how this works. So it adds fuel to get the RPM up, and it pulls the air down. It keeps the low control valve from opening all the way to keep the temperature cool. So if you've got a good, healthy APU, this valve can pretty much remain open and the RPMs are good and not really have an issue. All right, so that's kind of how these APUs, and this is the same for the 150. So let's get into these APUs internally. So we have a 36-100 shown on the left, a 150 on the right. And these are considered a modularized APUs. In other words, the gearbox sections, like this blue area here, just like it is on the 150. Power sections to compressor turbine, again, going the same speed. And by the way, these APUs rotate at a speed at about 60,000 RPM, so they're really a high-speed machine. And again, the big difference between the 100 and the 150 is that the 100 has a single combustor with a single fuel nozzle. All right, just one combustor. So this hot section can get a little bit more distressed than the 150 because this hot gas is coming in one spot, as opposed to the 150 that has an annular combustor system. So the hot air is coming in around this turbine nozzle much more evenly, and it has 6 fuel nozzles. So how this APU operates, we have air that'll come in through the center, through the Swiss cheese housing call, or the compressor inlet housing. It comes around a bell mouth, an inlet shroud, into the leading edge of the compressor. That air is now going through a diffuser, which is a fixed vane, okay? And this low control valve, in this case, let's say, is closed. And that air is going through this vane. It goes through another vaned deswirl, which does what it says. It takes that turbulent air coming through that first vane ring and deswirls it and calms it down. That air is now filled up this turbine plenum full of air, and you can think of that now as an air compressor. And now that's high pressure air, and it's trying to get to the low pressure, which is the exhaust. So that high pressure air, the only way you can get to that low pressure is through all the holes of this combustor. There's no other way to get to that low pressure. So it has to get through the holes. It then mixes with the fuel. Of course, we have ignition. And that hot air is now a reverse flow. It's coming forward. Unlike many turbine engines that the air goes straight through or maybe even centrifugally through, this APU has a reverse flow. So it comes forward for a moment, then to another fixed turbine nozzle vane, hits the tips of the T-wheel like a paddle wheel on a boat, and it gets the T-wheel spinning, which then in turn, of course, turns to compressor. So there's your 4 stages of compression. And then that air, once it hits the T-wheel, it expands out the turbine or out the tailpipe. So that's kind of how the air flows through this APU. On a 150, it's very much the same housing, compressor. Most of your common classic design, which we're going to talk about, there's 3 different compressor designs on the 150. Unlike the 100, which has just one basic design, the 150 has 3 different types of compressor sections we're going to cover. But on your classic design, which is the FW, BD, CX, A, or these models up here, That doesn't mean they're old APUs. It's just a basic design, classic, simple design 150. So again, air's coming through. It's going through a fixed diffuser, going through a D swirl, just like the 100. But instead of it going into a single combustor, it's going to an annular combustor system and 6 fuel nozzles with a nice even spray pattern. And that air, yes, is going forward again. That reverse flow is still in effect. Goes through a fixed turbine nozzle and then out the tailpipe. All right, so that's kind of how this. And yes, this also has a low control valve on it, like the 100 does. It's not in the picture. It's probably been cut away. So that's the 100 and the 150 classic basic design APU. All right. Now, because of that reverse flow situation, this APU has the tendency of wanting to stall. If there's any kind of hiccup or any kind of a lodging of particle or anything blocking this air from getting through, or maybe it's just on a good quick stall margin, this APU can surge and the air can come forward out the compressor, and we don't want that. So Honeywell has installed surge control valves on that plenum, and they're in various locations depending on the APU model. Like, for example, on a CX, it's mounted right to where the low control valve would be up here, and it's just kind of bleeding just below the low control valve. So the ECU will control the function of the surge valve. All right. So very simple. It's just open during certain operations. Honeywell knows when these APUs primarily want to stall, and a lot of times it's during APU start. And then this valve will open and close depending on the circumstances. All right, now here's a second type design. And this is called the 36150 variable geometric diffuser, or the VGD. We all say, variable geometric diffuser, but it's also a variable guide vane diffuser, right? You may know it as that, but Honeywell calls it a variable geometric diffuser, VGD system. Now, this system does not have a surge valve, and this you'll see on a Falcon 2000 with the 150 F2M and the 36150 RJ, which is in your Challenger RJ, the regional jet. All right, same kind of idea. The F2M is a little bit more advanced. It has more indications on it to allow it to meter air rather than on and off like the RJ. So what this has a variable geometric. So the diffuser is not a fixed vane in the compressor. It has, each vane can move 0 to 8 degrees angle from this actuator. So we got an air actuator that has taken sensors from the pressure of the plenum, inlet temperature, inlet pressure, and it moves this actuator, which then moves a lever rod, and inside the compressor is a variable guide vane diffuser, all right, the BGD. And the ECU really controls this thing quite well. It knows what vane angle to put it at various temperatures and pressures that it's given. And it does well. And because it has the variable geometric diffuser that kind of allows air to flow as it may, this APU does not need a surge valve because surging is controlled with this variable guide vane diffuser. So the reason for this, it enhances air. Like when this APU is running with no load, the guide vanes don't need to be open. So the APU is just running nice and smooth and freely. And now when you open up the low control valve, which is kind of typically where this cover's at, when the pilot selects air open to do a main engine start, pressure drops in this plenum, which is sensed off this little P3 sensor, and that tells the VGD that, yes, we got air with load, pressure's dropped, and this actuator now opens up those guide vanes to let more air flow through this APU to give this aircraft all the air it needs, all right? And it's pretty much the same operation for the RJ. It's a little smaller actuator. It's not a variable actuator. This one's either open or closed. It doesn't have all the sensors other than the P3. But operates pretty much the same function. So if you take that APU and take it apart, inside here's your compressor. You'll see here's the compressor rotor that sits down inside the shroud area. This here is a picture of the back of that, so give you an idea how this thing sits. And if I take this top off this compressor diffuser, you'll see all these variable guide vanes in here, and they all operate the same using one lever. They call it the unison lever. So one lever opens and closes these vanes using this actuator that's mounted to the side of the APU, and that's our connecting rod with the bearings on each end. So this gives you an idea of what that looks like inside. All right. So it's a very good system. It enhances performance. But as you can see, there are a lot of moving parts, lots of moving parts. Therefore, there's a lot of things that can go wrong with this APU. Now, on the 36, the last version of the compressors for the 150 is what they call the ported shroud. And this came along because one of the issues they had is the 36-100, that small APU used to be in a G4, which is a very large aircraft, also in the Challenger 600 series. And the hot sections would burn up quite freely with that 100. It was just too much air need for this APU to supply that large aircraft. And the APUs were burning up pretty quick. Hot sections weren't making it to its interval. And the 150, of course, seems to run better, which you seem to find these in a lot of your mid-size aircraft. So they got a lot of air for mid-size and a tiny APU for the G4 and the 600 series. So Honeywell came out with, and working with Gulfstream, and of course working with Bombardier on the 100E for the, they said, let's go ahead and use the gearbox from a 100G, for example, and marry it to a 150 compressor or plenum. So they took the gearbox, which is fine because that all hooks up nicely to the airframe. There's no need to overhaul that or change it. And let's put a 150 hot section on a 100. So they came up with this sort of a Frankenstein APU. So this is what they now put in your G4. Similar thing with the G450 and the G, those larger Gulfstream aircraft, and the Challenger 600, 604 series APUs. But when they do that, they call the 100E a 150CL, and the 100G is a 150G. So that's what they become, all right? Now, the ported shroud has an additional feature. Not only did they enhance the hot section, they also actually machined a port in the inlet shroud of the APU, which allows air to come in through the front as well as through this port. So this kind of operates like the F2M does. It pulls air as needed. And does not need to pull air if it doesn't need it. So what this APU does, it makes it a very enhanced, strong, powerful APU when it's got a load on it, and not so much needed air when it doesn't. So this kind of does simply the same thing as that F2M does, but no moving parts. All right, so this is a pretty good design, and it works very well. It has some of its issues with erosion in the compressor, and we'll talk about that. So here's the actual picture of that port. This is the typical compressor wheel you find in most APUs, but at ported shroud, they got a much larger compressor rotor, thinner vanes as a result of the larger size and what the vane thickness is on these, and that's why they erode relatively fast. But this is the air, so air's coming through this side area, and it's also allowed to come in through the side of this inlet shroud. So this thing gets more air as needed, and not so much air if it doesn't need it. Talking about the gearbox. The gearbox are pretty much the same function, just a little differences. All right, so this is what you're going to see on the 100, and because the 150CL ported shroud we just talked about in the G used that gearbox, this would have the same kind of idea of the gearbox on those. Are the only 150 models that really have a 100 gearbox on them. Most all your other 150s have a gearbox that sort of looks like this. Okay. There are some goods and bads. For example, on the 100, the oil pressure regulator is in the gearbox, so you can't do anything with that in the field. The oil filter is a very difficult area at the bottom of the gearbox. It's really difficult to pull that because they're so close to the containment box. The oil pump is inside the gearbox. One good thing they did do, though, they have to where you can replace the generator gear shaft if you get worn splines on it. You can pull this front adapter off and pull the gear out and do whatever you need to do to it. All right. So when they made the 150, they enhanced some of these things. For example, the oil pressure regulator is now an externally removed item. Okay, you can pull it out of the side of the gearbox. The oil pump can be changed in the field. It's an external item instead of an internal. All right. Oil filter, much easier to get to at the top of the gearbox. Where they went backwards is on the generator drive spline. So again, if this one has worn splines, there's no mount pad to pull off like this one. To get this gear out, you have to pull the gearbox off the power section and pull it out from behind. So they made a lot of positive moves and made one negative. And so to be that the 150 seems to have more issues with spline wear than the 100 does. So it's kind of a, kind of a wicked trade-off, but that's the case. But other than that, it's pretty much the same function as they both have. Now, on your typical 100 series and 150 classic type APUs, again, the gearbox operates the same. All right. So here's what we're looking at. We have an oil pump inside the oil system. Okay. This is the back of the gearbox. You take the power section off. This is what you'll look down on inside here. This is that large gear that has the splines on it. You would pull out from the back if it was a 150. All right. So the APU's oil system holds about 2 to 3 quarts of oil, depending on the model. Has a single stage oil pump. There's just 2 little oil pump gears inside to spin. The faster it spins, the more displacement it has. Very simple. It's an oil jet squirt feed system. So there's a lot of ports and little targets of oil, and it squirts the bearings. All right. So as this oil pump delivers the oil, it goes through like an oil manifold and targets these bearings with oil to keep them lubricated. And there's no scavenge return. All that oil just drips back to the sump and starts all over again. It just drips back. Okay. So there's no like second or third stage of this oil pump that pulls the oil back to it. It just returns just like a lawnmower engine. The oil is cooled by these fins, which are located back in here, and there's fins all around the front housing, which is all here. And this is all encapsulated with the compressor inlet shroud. So as air is passing through this, air is going by these fins, keeping the oil cool. All right, but the main thing I want to point to, an oil temperature is not a big issue for these APUs, and that's because of this cantilever design power section, which I'm going to talk about, which means there's no bearing in the turbine. There is another type of oil system, which is typically found in the RJ and the 150 G4, which is, your G450. And that's because they have a large, here's our gearbox, much different on those 2 APUs, has a large generator on the front, and it shares its oil system with the APU. Because it has that extra capacity and oil has to be pulled back from the generator, this oil pump has many stages. All right. There's this could be a 4-quart oil capacity, 5 stages of the oil system, 2 stages of pressure, 2 stages of gearbox scavenge, and 1 stage scavenges just the large generator that's mounted on here. Again, it's air cooled. This is air cooled though by an external air oil cooler mounted on the side of the APU, and it gets this air from a cooling fan that's mounted up here in this cavity, spins, and that's actually a fan inside hooked with a rubber duct, which hooks to the front. So as this APU is running, that fan's actually cooling the air going through the oil cooler. So again, a little bit more elaborate, but again, cantilever design, which here's what the cantilever design is all about. Most of your turbine engines are built sort of like it's an actual stage turbine. And in this rotating group, turbine and compressor have support bearings, cradle bearings, one in the front, basically one in the middle, and they'll have one back in the hot end. All right. Now, because it has a bearing that needs oil, that oil is right next to the heat of the hot section. Here's an old Dart engine, which I used to work on many years ago. Same idea. Here's our front support bearing. Compressor is in here. We got a rear support bearing of the power group. And back here's another bearing back by the turbine. Again, that hot air is right on that air, and as that oil comes back, it's heating up the oil just by the fact that it's next to the hot section. But on a 100 series APU, and here's kind of a blown up picture, here's our turbine, here's our compressor, and the last bearing is at the front of the compressor. And our thrust bearing, support bearing, thrust bearing is up in the gearbox still, which is up in here. So you can see there's no bearings in the turbine. The last bearing is at the face of the compressor, which is a cool area. So we don't have oil getting heated up by the hot section. So oil temperature issues are not a big problem with these APUs unless you have some kind of bearing that's kind of wiping out on it. So that's the cantilever design, meaning the power section is hanging off cantileverly from the support bearing and the thrust bearing. So it's a pretty unique design, and that's why one of the issues with oil temperature is not a problem. So things to look for on this APU, some of the be careful kind of things that pop up. And these are the pretty most common ones I'm going to talk about. One is the starter motor. So these APUs, a lot of these APUs we're talking about that have this Bendix type little black starter motor, and it's mounted to a clutch pad up here in the top of the gearbox. So we're talking about these models, the 100E in the Challenger, the G 100M, the 150BD and the Challenger 300, 350. The CX and the Citation 10, and here's our ported shroud APUs because they use the same gearbox as the 100E and G, and we got the 150 and the 150M. All right, so we're talking about any APU that has this little black starter motor on it. All right, now this starter motor hooks up to the front of the gearbox, and there's a clutch inside the gearbox. Okay, and sometimes what happens is you'll hit the APU start button, and nothing happens. It's just dead in the water. You've done this, you've done that, and then you go back there and you're like, oh, I must have a bad starter. So you replace a starter, and the APU will start up again. All right, but the next start, it's failed again. So if you pull back the brush block covers, and here's what the brush is typically lying against the armature, the commutator of the armature. Well, if you could dump your brushes out like this in many pieces, then you had a situation where the starter motor wasn't able to disengage from the APU after the APU started and started running. All right, and what happened, because the starter motor was still engaged into the APU as the APU is running, the speed of that APU, the starter can't take that speed. So what happens is the commutator, which is that brass solid portion, many blades, starts getting out of shape, and it becomes a chipper, and it starts chipping your brushes away to the point that it's not any good. So the problem is when you see this, all right, that means you have a clutch failure. And here's our clutch that's inside the gearbox. You'll see it's in this cavity, and it's a Sprague clutch, and it's quite there's quite a bit to this. But this shaft is hooked to the starter motor, and this gear runs with the drivetrain. And the only thing that connects these two is the starter clutch piece right here. And this is a Sprague clutch. So once this thing senses RPM, these sprags come out, and it actually binds the shaft of the starter motor to the spur gear of the APU. Now, as this APU is wanting to start, this shaft spins with the starter. All right, the Sprag immediately senses that RPM, and it locks the spur gear to the shaft and get the APU running. As the APU runs and the speed becomes greater, and the starter motor is kicked offline by the electronic control unit, which is about 60% RPM, then this shaft should come to a stop with the starter shaft. But because this clutch is wiped out, it actually still sees the two pieces together, and it won't disengage. Therefore, the APU is running, the clutch has failed, it's hanging on to the shaft still, and therefore this starter continues to spin as the APU runs. And then, as you saw in this prior picture, the brushes wipe out. So in the maintenance manual, it always says, if you're going to replace a starter motor, do a clutch inspection. All right. Now, the clutch inspection is just by means of rotating this clutch with a screwdriver, and you can open up this, on the end of the starter, this little triangle plate that has a screwdriver slot for the armature. You open that plate, put your screwdriver here, and you can spin this starter, and the whole gearbox and everything, the gears, the turbine wheel, and all should spin nice and freely. And when you rotate the screwdriver in the opposite direction, nothing should be spinning except for this shaft, and this clutch should be allowed to be free. If this whole rotating group and everything's spinning as you go in the opposite direction, then your clutch may be failing. That prevents you from putting a new starter motor on a bad clutch unknowingly and wiping out your second starter. All right, so if you have a failed starter, they always tell you, do the clutch check, because you don't know why it failed. Did the starter fail electrically, or did it fail mechanically? Electrically, okay, great, they fail electrically. But if it's a mechanical failure, you may have deeper issues in this gearbox with this clutch. Another thing is low oil pressure shutdowns. There was a problem with oil filters. Of course, we would check pressure on a direct reading gauge to make sure our oil pressure is okay, and so on and so forth. Or if we're actually got an indication problem or a bad oil system. Could be oil foaming, which sometimes is caused by a silicone contamination, that RTV or something got in the oil system. But a big one was these oil filter restrictions. So there are, as a service information letter out, APU 153, which a company called Western Filter Corps made a PMA filter that was too tight. It was restricting even the cold oil, and we were getting low oil pressure shutdowns. And there was another filter from PTI filters, and service bulletins out about that. We had the same issue. All right. So when you order a filter, you order a Honeywell number, but you don't know what vendor it's coming from. So pretty much everybody's purged their inventories of the PTI filters and the PMA filters. But if you're having low pressure shutdowns and you're getting a filter from some unknown company that's making a PMA, and we're talking primarily for the 100 series APU and these two 150s because of, again, same gearbox. We're talking these APU models, not the normal 150s, the classics. You might want to check these bulletins in this service information letter out. Another issue all 100s have, A's, E's, and G's, is we have stalling or surging that occurs with the bleed air load off. So at this point, the low control valve is closed. We have maximum air pressure built up in here, and all that pressurized air needs to get through that turbine nozzle and out the tailpipe, like I mentioned earlier. But if we have a diffuser, which is up here in the compressor, the vanes, if we have a diffuser that's compromised, it's eroding back, it's got erosion and thinning, this diffuser can't hold the air back here. So that air wants to come this way and cough out the compressor. So if you're having compressor stalls, and again, bleed air off, when you open up the valve, that relieves a lot of air, so you typically don't have the issue. So when you have no load air on, load air is off, and you're getting this popping and surging, and your surge valve is operating fine, then it may be you have a bad erosion on your turbine nozzle. So you can actually do a bore scope deep and look for this erosion in the vanes, and this is what it would look like. Same scenario, stalls are surging, again, bleed air load is off, valve is closed. Well, these 100s and 150s are notorious for making carbon chunks in the plenum, and they'll just like a big old charcoal chunk, and it'll break off, and the next place it wants to go is downstream and get lodged in the turbine nozzle vanes, which is that last vane nozzle, and you'll see one here, and that creates a restriction. So that reverse airflow that we have, which has to be a nice flow out the tailpipe, is now getting restricted. And all it takes is one of those vane throats to be clogged off with a nugget, and this thing is going to surge and pop. All right. Open up the valve, and it relieves enough air pressure where you typically don't have that problem. So to fix this, we would have to pull the plenum off, clean out the chunks, make sure that's all okay, and hypothetically just change the fuel nozzle if it's a 100 or the 6 fuel nozzles on a 150, and we would also change the combustor or the annular combustor, and what caused it is unknown. It's just an issue. Honeywell's come out with service bulletin for fuel nozzles on the 150s to help combat, and jury's still out on whether that's going to fix or not, but it's just cold air coming in touch with a hot surface, creating these carbon chunks, and it breaks down. So if you change the fuel nozzles and the combustor, sometimes that combination works. Okay, so that is an issue. So we're just talking about this ported shroud APU again. Again, this is that one that has that side port, the 150 CLG. There's other APUs, the ported shroud. And I mentioned this is a large compressor wheel. However, it is a thinner vane. And so this APU, because it's pulling air through the front, which is through this way, and through the side, which is here in the side of the APU through that port, as environmental debris, sand, whatever is coming through, it's wearing away at the compressor wheel. And you'll see this is blade root erosion, and you'll have side contour erosion. These notches you see here is not normal. When you get this compressor wheel new, this is typically a straight area as well as this, and they call this fishhook erosion. Okay, now you are allowed to have a lot of this providing there's no cracking in a bore scope inspection. All right, they're not concerned about this providing there's no cracks or anything ready to break off. Here they're a little more concerned because this is where a lot of these blades get flex, and they're afraid a big old piece of this is going to break off. Now there used to be no damage allowed in this area, but now they relaxed. I think it's 30 thou worth of erosion, if I remember right. Go to the book to verify, but they will allow some erosion here, and they allow a lot of erosion here. So providing performance is not affected, they don't have any issues with this, and there's no cracks, and performance is good. Up here, they don't have issues with it as long as it stays within 30 thou, but this is a high dollar component, and they are scarce to find. That's the big issue with this 150 ported shroud APU. Honeywell is just not producing these wheels like they need to, because they're finding this corrosion to be a real problem. So something to think about, but there are allowances now. Honeywell, I guess as supply was becoming increased, they relaxed their limits on what they're allowing to make up for the lack of supply in the compressor wheel. But still, I've only seen 1 or 2 of these come apart, but they were extremely bad and probably should have been caught long before they did. So, but that's one of the issues you may have with the ported shroud APU. On an F2M, our variable geometric diffuser compressors, You could have a situation where your EGT momentarily rises into the red during main engine starts and slowly returns to normal. And what that's indicative of is those variable guide vanes are slow reacting. They're not reacting very quickly. Again, lots of moving parts, okay? So you may have a sluggish actuator. Maybe the diaphragm inside is just not, maybe it has a rotor getting stiff, all right? So it's not reacting that actuator very well. On the end of the actuator rod that's connected to the actuator, to the guide vanes, is that rod that has two bearing ends on it. Well, maybe they're starting to rust and seize up. On the end of that main lever, which is your unison lever, there is a bushing that perhaps it's seized up or broken. Or ultimately, and the worst thing could be, is that the actual assembly itself, all those guide vanes are starting to get eroded and seizing and move. So if you have a sluggish movement of this variable guide vane, you'll get maybe air rising in, your temperature rising into the red until that guide vane actually pulls open to let air through, and then it finally returns to normal. So this is a situation. Now, all these items can be fixed. So here's our actuator. That can be a problem. That can be replaced in the field. The rod ends that I mentioned can be eroded. They can be replaced in the field. Even this main lever bushing that's deep inside the compressor area, and here's the bushings on the end, could be a graphite type bushing or a stainless bushing. And this one starts to corrode or this one breaks. You can even get to this bushing to replace that in the field. And in fact, you won't even need to pull the APU out of the airplane on the F2M. You can just replace these in situ. Now, if you have where your guide vanes are all corroded, that's a shop visit. All right, that's got to come all apart. They got these graphite bearing or bushings that got to get replaced, and it's quite expensive. But just know, if you have a Falcon 2000, you're getting that issue, we can do a lot of things out in the field to help that. And there's service bulletins about all these things, all right? But this is a shop repair. Delayed starts. We can have a situation where we got fuel, we have ignition, audible ignition, but on the 100 series, we may have a mispositioned combustor cap. Igniter plug's very short. If you look down in the combustor, and if you don't have this thing positioned right, you get too far away from the fuel nozzle, and you'll get all the fuel, you'll get the igniter snapping, but they're just not coming in touch with each other. And that's caused by the cap having these large holes with a 1032 bolt going through it. This cap can be moved before you tighten it down. If you're changing the fuel nozzle, you can slide this cap around a little bit, which actually pushes, here's our igniter plug, which is threaded to the cap. You can actually push this igniter plug away from the center fuel and bolt it down and not even know you did it. And so you'll get fuel, ignition, but the plug's too far from the fuel and it won't light off. The other problem that can cause the same thing is if, here's where the igniter plug's threaded in, you can have a bent igniter plug boss. So you have fuel, ignition, but because this boss is bent down, the tip of the igniter is up here. Here's our spray fuel, and the igniter again is too far from the fuel system. Delayed start. So something to look for is that bent. This is a very common issue. These get really thin metal down here. Oil smell in the cabin. Most of you that have this APU know all about this. We have compressor seal leaks. So up in the head of the compressor, here's our compressor. We're looking through the bore scope of the inlet. Here's that front support bearing. The last bearing is at the head, and right in front of that front bearing is a carbon seal, and they leak, and you get oil that seeps into the compressor section. And you start smelling oil in the cabin cockpit when you got the bleed air on. Got the heat and air conditioning, and you smell oil. So this is like an oil stain. If you can see its wetness, you'll see some drips maybe on the compressor. This is something that's an issue, very common issue. This can be fixed in the field as well. We have mobile service that can be dispatched pretty much nationwide. If you pull the APU out, we can get this out of here and split it, change the seal, put it back together for you. All right. Oil venting overboard. This is a big one. This happens quite often. And what the deal is on these APUs, if you look at the gearbox, which is up here in the blue, this APU gearbox is fully sealed up. This is a sealed cavity. You have a compressor seal up here in the head of the gearbox. You got O-rings and shaft seals on the starter. We got seals on the generator case. We got seals on the FCU. Everything's oiled, dipstick O-rings, seals. So this gearbox is completely sealed off. Okay. The only place air can get in and out is through this little vent tube on the front of the gearbox. And that's where air can come in and out. So whatever the outside ambient pressure is, should be the same as what's in this gearbox. And because it doesn't have a scavenge return oil pump sucking oil back, it doesn't create a negative suction in the gearbox. So air just allowed to flow in and out, all right, of this here vent. And as long as, you know, everything's sealed up properly, there's nothing that's going to come out of this vent. Oil should not come out of this vent. You just should have air that comes in and out. You may have a little bit of misty oil, but nothing draining out. Like, so this here vent typically goes overboard into a belly drain. All right. They have modified that in some cases. We're on a 100. This is just an open vent. All right, goes to a fuel, like a number 4 line, flex line, goes to an overboard drain in the fuselage. And everything should be fine as long as everything's sealed up. But sometimes what happens is you come outside of the plane, you got oil all over the tarmac, and you see that belly drain has oil coming out, and you're wondering where the heck's all this oil coming from, all right? Well, what's happened is something's compromised. Somehow an external air source, an added air source has gotten into this gearbox, and now oil can flow out the gearbox. So, for example, as you're flying, and this is on the end of a fuselage at the drain, air going by that tube can create a negative suction in this gearbox, and it can suck the oil out, but it can only do it if it's not deadheaded. Because this is a sealed gearbox, this is a deadheaded system, so oil still can't be sucked on this thing or sucked through that. But if there's air allowed to come in through any one of these seals, now you can have oil that flows through here. So let's talk about how this actually works. So I look at the gearbox as in the simplest form, like a child's drinking cup. And if you'll notice, a drinking cup on a child's cup doesn't have an oil vent in it. It's just, that's the only opening is where the draining's coming from, the drink's coming from. And as long as that's deadheaded, this child has to really draw on that cup to pull fluid out of it, to get the juice out of it. And if that cup falls over, typically nothing spills because there's no air vent that lets it continue to flow out. Unlike a coffee cup, which has the opening on it, and you got a little vent hole, that's what allows the coffee to flow nicely, you know, out the coffee cup. Same thing here, there's another vent here, all right? So these coffee cups this is the kind of a drawing of what, or a diagram of what's wrong with your APU if you have oil flowing out your vent line. This is what you want, all right? So as as you're drawing on this, if you don't have a hole in that, you're not going to get much coffee out of it, just like this. So basically, in the end, if your oil system is venting oil board over, or oil venting overboard, you have an air egress in your gearbox. So what we would do is we would put a vacuum pump right on that vent fitting, out of that one vent fitting on the gearbox, and pull vacuum. Lock the vacuum in and see if we lose vacuum. If we do, we want to look around or listen for a hissing sound where that air is coming through. And once you fix that and get that gearbox back to being deadheaded again, your oil flow will stop. And on the 150s or 100, some of your gearbox vents, instead of going overboard, here's that vent here. Gulfstream, for example, is running a steel line to the tailpipe to burn off like the residual oils that you may have had, like just typical misty oil. It goes right to a fitting on the tailpipe. All right, and that's a service bulletin. All right, now the problem with this is because it's burning oil off of the tailpipe and it's not showing a witness going in the tarmac, you don't know that this system's oil venting. All right, because there's no indication of oil in it because it's getting burned off as the APU's running. So your first indication of oil venting on this APU is that you have a low oil pressure shutdown because you've actually sucked all the oil out of the gearbox until you no longer have oil pressure. And at that point, you need to start doing some troubleshooting in the same fashion. Okay, so it's a great system. It prevents all that ugly oil residue on your fuselage and whatnot on a normal operation, and it burns off the residue on the tailpipe. But it does take away your troubleshooting indication that you're having an issue. All right, so if you lost all your oil, low oil pressure shutdown, lost your oil, and you don't have any external oil leaks to prove that you've lost oil externally, it could very well be you just sucked it out of the tailpipe. So we got to find out where that gearbox is getting air egress into it, fix that, and that situation will stop. You got to get this gearbox deadheaded. Now on the 150, they enhanced that design. So like I said, on the 100, it's just a line from the gearbox to the tailplate. On the 150, they said we really actually would like to have suction in that gearbox. So they actually put what they call an ejector fitting on it. So it taps, it's a three-way valve. It's the same as the 100. It's oil coming from the vent of the gearbox. And if you look at this, it goes to the tailplate, just like that last picture on the 100. But they put this ejector in and they actually tap pressure off the plenum, which shoots air through this ejector and exhausts to the tailplate. But by shooting air through this, as you'll see right here is air, it's actually pulling. All right, so here's the P3 coming off our plenum and it's going to the tailplate. So when you have air going by this fitting here, it creates a suction on the gearbox. And again, that's awesome. It'll actually suck your gearbox down to about maybe 6 inches mercury, 6 inches Hg, which is good. It's good to have suction in the gearbox because it helps keep things sealed up. It helps your carbon seals and Garlock seals from leaking. However, when this system decides to vent, because we've got an air egress, whatever the case may be, because it has suction, it pulls your oil out of your gearbox quite quickly. And again, you don't see any evidence of that because it's burning it off in the tailplate. So this system kind of will depending on how bad your air egress is, this can pull 2 quarts out, heck, maybe on quite a few flights, where this one, with the suction added to it, can pull 2 quarts of oil out very quickly. I mean, you can also lose all your oil very quickly, and it's a done deal. You're not doing anything. Okay, so something to think about. And the other reason why we call it looks like also here we are again. This is a 150M, I believe this one is. All right, yeah, this is a 150 or 150M. Again, same gearbox with the vent fitting, and here's our tube going to an ejector system. One of the issues this has is, and the same thing with any of the 100s that have this little vent thing, it's like an L-shaped tube that's been out the front of the gearbox, has a little tube that goes inside of a gear. So there's a gear spinning real close tolerance to the end of the shaft. It's like an air oil separator gear. And this tube can get bent. And when that gets bent, the tube can actually scrape the inside of the gear that has oil in it. And it's not really sucking oil out, but it's scooping oil out of the gearbox. So you'll get like a very minor, you'll be losing your oil. You will lose oil. It'll burn off in the tailpipe. Not quite as much as oil getting sucked out, but it's getting scooped out, but just a minute amount. But that's something to think about. If you're having oil venting overboard and you ruled out vacuum leaks and whatnot, or air leaks, it could very well be the end of your tube is actually bent and it's scraping the oil out of the gearbox and making its way out the tailpipe. So these are pretty common issues you'll find with the 100s and 150s. Of course, there's quite a few more, but these are the ones worth covering because these are the most common that you see out there. All right. And that ends my presentation. If you have any questions, I'll be free to answer them. And thank you for your time and have a good day.